Hello, and thank you for joining us today. As we series today, we talk about how to create a pressure controller calibrator uncertainty budget. If during this presentation, please use the chat or Q&A feature in WebEx to send those questions to all panelists. The chat feature actually works the cleanest, so I recommend using that one. Once and send it to all panelists, and then both can answer. A the presentation and a the recording will be sent out later this week to all who attend. Today is Mr. Josh Baker. He is a flow metrologist for Fluke Calibration. He has 12 years of experience in calibration, first with the U.S. Air Force, and now Fluke Calibration. Josh has become somewhat of an expert on training budgets and specifically when you're using a pressure controller and presenting at the National Conference of Standards and Laboratories International. Further ado, I present Josh Baker. Thank you.
As stated, my name is Josh Baker. I'm a pressure metrologist here at Fluke Calibration, and I gave a presentation a few months ago. Made changes to it based on some feedback and questions I received, but if you've seen this in the past, it's kind of a refresher. If it's new, I hope you enjoy it. The webinar is going to be based on how to create pressure controller calibrator uncertainty budget. About pressure controller calibrator specifics, the component certainty, and any additional factors you should consider when using it as a standard. So we propose an instrument that can set, control, and measure pressure. Commonly referred to as secondary or transfer standards in the industry. Pressure calibrators are generally used to calibrate other secondary standards or manufacturing production environments to calibrate items which are at a lower accuracy, the pressure calibrator. Controllers are segmented in the market by their uncertainty class. Different types of uncertainty classes for the pressure controllers determine their price. They utilize various sensor technologies. Shows a few of the pressure controller calibrators that Fluke manufactures. Some are acquired from Rustermans, some are new. If you look at the Rust 7250 series, those use quartz board on tubes, which is a high-end sensor technology. The DHI Fluke PP4 pressure controller, those use the quartz resonant pressure transducer, or QRPT, and our models like the 4022 box on the modular controllers. Those use resistive, and the focus of today's presentation is going to be on the newly released 6270A, which utilizes the modular PM100 and PM200 pressure modules. And the uncertainty we're going to go over today is in the QRPT version of the PM600. All right, begin. I find these 4 steps here are a starting point in starting an uncertainty budget for your pressure controller. Just gather information about your pressure controller, reference standards that were used to calibrate it, identimeters in your laboratory or the environment that will influence your pressure measurements. You need a magnitude of all the uncertainty contributors, and you'd be able to combine all of the uncertainty contributors into an overall certainty statement and confidence interval. So this is pretty much our goal. What you want to come up with is a itemized budget of all uncertainty parameters, the type of distribution, the type of uncertainty that they're presenting, their distribution type, their interval, any information that helps somebody just look at this, see what it is beneficial. Notice I have parameter type, percent of reading, percent of full scale. I have where I'm getting the uncertainty source from, whether it's a calibration report or a specification or from a test. I use a freedom on that computer, and I list everything at one standard uncertainty. Standard uncertainty for the type of uncertainty we're talking about, either relative or threshold, and then our goal report at 95% confidence about each one of these contributors as we go through the presentation. Add a little bit of Jeff's uncertainty show, just to kind of give a general overview of the different I listed in the uncertainty budget. So, uncertainty. The definition of uncertainty is a number that characterizes the dispersion of values attributed to a measurand based on information you have at hand. Now, it is a intended to be measured or the object you're trying to measure. It is, we're talking about interval about which the measured value, the true value lies within. So this slide represents a true value that is really unknown and really unknowable. And of the measure plus or minus an uncertainty, we hope that we're capturing the true value within that uncertainty band. I want to mention that uncertainty can be derived from many general knowledge, experience, scientific judgment, integration certificates, manufacturer specs, even analysis, and a lot of the times just a series of observations help determine the uncertainty of a parameter. Now it's defined as the uncertainty of the result of a measurement expressed as standard deviation, which is known as 1 sigma level of confidence. And there are two methods of evaluation, which are type A and type B. The evaluation is specifically defined as a method of evaluation of uncertainty by the statistical analysis of a series of observations. Uncertainty that are evaluated by type A are variance, noise controller, environmental factors, anything that you can't control. It's not systematic. It's conditions and drift over time can be into this type A evaluation. I plan to kind of represent how measurements and degree of freedom that you have can affect your uncertainty. And you see at the bottom, 5 measurements, I have a wide spread for my uncertainty. As that bell curve just becomes clear. So the more measurements you make, the better you will have, and hopefully the uncertainty you will have. A single standard deviation of a normal distribution looks like. It represents 58% of the curve. Yet all of our contributors at this level when we them. Evaluation is a method by the means other than the statistical observation analysis of observations. You can be from the uncertainty standards used from the calibration report, due known resolution of the item. Corrections are used as a type B uncertainty. Distribution, bell curve. Just basic types of distributions I have in this uncertainty budget, which are normal and rectangular. There's many other types. There's triangular, U-shaped, equal, but we're going to be talking about normal and rectangular. Solution is a distribution that arises most commonly from the measurement process. And when you have several distributions are combined, they eventually become a distribution. Form distribution. These are from factors as resolution, where you're plus or minus a digit, or when the source uncertainty has little or no information about them. As I mentioned earlier, there's other types such as U-shaped, triangular, but I just want to keep this discussion based on the type that are used certainty budget. Now, if you want a standard uncertainty, there's a divisor for each. You would buy the coverage factor. This is a calibration certificate, and it's found a divide the coverage factor noted on the report. Typical distribution is square root of 3, which is 1.73. We talk about uncertainty components, type A and type B methods, standard deviation, and now to combine all contributors into a single value. So I have the uncertainty contributors at 1 sigma times K, which is going to be the coverage factor. Applies for infinite degrees of freedom. Budget I use the Satterthwaite formula with student T table to combine all my contributors and their degrees of freedom to ensure I can use the number 2 multiplier. Otherwise, it doesn't have to be 2. It could be 2.3. It could be 4. But my budgets, I always try to with contributors to ensure I can use 2, so I can state what I'm actually using as my K factor. All right, now we're going to uncertainty budget, but here are all the parameters that I had listed in the early slide of the spreadsheet. So the uncertainty, the percent of the measured distinct element, and that includes and the stability of the sensor, stability, which is the stability and zero drift stability, fluid and precision, competition, which is attributed 6 product that we'll be talking about, and type A uncertainty contribution. So the use uncertainty is dependent on the pressure range of the QRPT. The QRP I'm using as an example is a APS 700 kilopascal or 100 psi sensor. So for the sensor, I chose a conservative reference. It's a page reference of 0.3% of reading scale for absolute load measurement. In the table, I have a relative portion and a threshold uncertainty portion. So put the rate uncertainty in the right. Here I have a relative uncertainty, which is B1 of 0.03% of reading, with the level from the calibration report, and I had because that's 95%, to get the last column on the right, my K1, my one standard uncertainty. Now for the threshold uncertainty, which is the error of the reference, Pascal, which equates to a percent of 0.0015%, and 95% confidence interval, trying to get 1 sigma. So I combine all of these. Decision and includes the following bullet, which is linearity, repeatability, and hysteresis. Is the error of nonlinearity, or linearity it's commonly called, the error from the deviations of the linear output of the pressure sensor. We'll take a single pressure point along the span of the sensor, so we point span, and in those points, we hope they're linear, but there are some linearizations in the linearity specification. Repeated is part of the sense spec, which is the ability of the sensor to repeat with the same conditions and the same in the same time period. And history is the mechanical measure. Sometimes zero drift of the sensor can contribute to hysteresis, which may make hysteresis larger. So to take away zero drift from hysteresis. So sometimes they're combined into one. For the QRPT, we have conformance specification of 8% of reading down to the threshold, and that's the main specification from the calibration report or our literature. So reported at the rectangular distribution, so it has a divisor than the precision threat uncertainty. But our goal is to get those to 1 sigma to be normalized. We have a QRP categorized into 2 parts: long-term stability and short-term stability. Long span or drift of the sensor and or the electronics is monitored, or interim checks, but corrected by adjustment. Short-term stability is zero drift, which can be realized by zero instruments if you're in absolute mode, and in your engaged mode, you're can be zeroing when you're vented, and that gets rid of any zero influence. Change from the previous presentation, I added the gauge and absolute threshold uncertainty. If you know that for the gauge mode uncertainty, 0, because every time you zero the instrument when it's vented, you remove the zero drift. Once it's gone. For absolute mode, it depends on how often you're zeroing 100 kilopascal sensor to a or a lower range sensor. So you include the uncertainty from the barometer that you're using, and yet include the stability, which it could be different. But you might have one A700K that drifts within its specifications every time you drift, and you might have one that doesn't drift at all. So it's good to measure your instruments so you know what their performance. Next, that's the specification of the sensor, which is part of the overall specification that Fluke delivers. Here, reporting distribution level and divisor to get to 1 sigma. correction done about how you can measure the height, the fluid being used, and how well you know the density. This has onboard head correction computation, base table, and the firmware density immediately select. Do is know how you can measure head correction with like your ruler or tape measure. So you can study in your lab on all your technicians, you find every technician you have can measure the head height within 1 inch. That's what I'm using for this uncertainty budget. So inch of uncertainty on measurement between technicians give me about 0.03% of reading error. To measure better than 1 inch, that's going to decrease. But see, that's a really relatively low number that doesn't up the overall uncertainty budget. So it's not worth trying to make somebody measure within millimeter, 5 millimeters if they don't have to. If you're in that, you're in some ballpark, you're good to go. Resolution should be considered for this is much insignificant on our final product uncertainty, but anything you want to consider, you should add it to your budget and document just so you can prove, did look at that, and you prove that it's not a major your uncertainty statement. And many of the PPC products, PPC 3, 4, RPM 4, just sensor, when you're in mode, you have to have some of dynamically compensating that gauge pressure on an onboard barometer. The PM has that feature. Real-time gauge pressure measurement without having to re-zero when atmospheric pressure changes during use. There's a barometer that is continually monitoring barometric pressure and adjusting or capture on your output. Here, for all contributors, even though you're not going to be using them, ICE holders in this budget, because control vision, I could use default hold spec in here to say that that's my specification. I'm using that. It's fine if you're using pretty much displayed value on the controller, but monitoring it through remote communications, you're getting the real-time pressure measurement every time you talk to the instrument. So to use that, I would have to have other factors to make sure that I'm always within that measurement band in the ready condition. Zeroed out for this purpose because pressure noise is at the procedure level, which I have reference certainty from this budget will be used. It will be combined with resolution of my device test and the control noise I get when I'm running the procedure. And it could be per dumb calibrating due to the instances from the device under test. I leak in my pressure system that I didn't have a week ago. That's why I always try to handle control precision at the procedure level, not in my budget. And today, control precision type A, which is part of very random results that you're getting from your pressures. In the environmental conditions, control noise, which I mentioned as control precision, how it makes measurements, vibration on the bench. You have a vacuum pump that's a bench failing, causing more vibration 1 week from next, which influence your pressure measurement results. Down the list of all the parameters for the relative section and the threshold section. The UR I have on the top line, that's the relative uncertainties, the threshold uncertainties. the idea is they're all at one deviation or one standard uncertainty. We're going to combine them all by root star RSS. All combined through RSS, we can find 95% confidence level. So the value for my 95% based on, I'll show you the spreadsheet. So the and its freedom for each contributor was to use the Satterthwaite formula to come up with effective degrees of freedom and the total uncertainties. And with an effective degrees of freedom, its weight of each contributor and its uncertainty, for K I might have 9, but that's 0 here, so it really doesn't influence me. But if you're a contributor and you impulse, and it aims your overall uncertainty where your K factor might be larger than 2. Making sure that this value, using the T inverse, student's T inverse based on freedom, I can use the value of 2 to multiply my standard uncertainty, which is my overall 95% for my relative threshold uncertainty. At 0.013% of QRPT span. When I combine 2, I get 0.06% of QRPT span. Slide just to see there's a lot on here for the slide, but you see how I annotate and dot each contributor, even not using them. Like for control, I have 0. Typo for the relative in the certainty portion. My stability, I can type A are all 0. It's that to make sure that the major significant contributors, like go through them, see if they're going to be used. If anything out, it's you know that from the audited for your quality control system that you always have documented of things that you considered and make notes on why you're not using it. Practice. Kind of got done a little bit early, but I'm not sure if there's going to be any questions. If you have any questions, they email to me directly. You can ask them in this forum. We all really report here that answers various questions on the product, technical specifications, and then if they can, uncertainty question, it usually gets forwarded to our metrology department. I'd like to thank you for attending, and I'll have some questions right now.
The first question we have is threshold uncertainty. Is it given as a percent of range or percent of full scale or proceeding? What is can kind of through the threshold uncertainty concept again?
Okay, this is pretty much a commonly referred to as a floor or an error, and this is not an adder. It's a kind of reading or the greater of the span whichever is later. So it can be stated as span value, the full scale value. It can be pressure units. Like notice I have double or 0.15% of QRPT span. If we're dealing with a A700K, that's going to be 105 kPa. If my specification unit here in kPa, I would have to ensure that I'm using kPa these values instead of per span. But in temperature, I think we're using QRPT span for this.
Do it or fluid correction for pneumatic controller / deadweight tester. With reference to the head correction.
You sure it? I think in our QRP, our pin gauge tech note, it's not considered because it was assumed that you can bring the device under test to the level of reference level of the piston gauge. If you're doing that, you really consider that. You should always leave the computer in your budget though, and put a 0 there, or put a comment that you considered it, but it's not significant. Significant at higher pressures, if the percent of reading, usually for gas, it's about 3 ppm per inch. So if you're 0, it really doesn't apply. But as you go up in pressure and the density increases of the gas, it's more significant. But no, if you say in your procedure, make sure your DUT's always brought up to the reference level of my controller, you really don't consider that.
Final answer is that as much as we consider everything, but since we're able to be at, or we find to be at an insignificant point, do you say that your head height is equal to ± an inch, ± centimeters? The additional uncertainty is 3 part per million, and if you're doing 100 part per million work, then 3 part per million becomes very insignificant size. Okay, why is the divisor different with the same stated confidence for the temperature and stability, 1.3 versus 2.0 respectively?
I'm looking now. Let me see. Temperature, rectangular, 1.73 for relevant. And for temperature, it's rectangular. Divisor 3. A divisor of 2 for temperature budget.
I think he's referring to stability, how stability is a divisor of 2. Although it's stated here as rectangular, I think there's a typo there. It's a normal distribution with a rectangular, normal distribution with a K equals 2.
See, that is a typo. If it's rectangular, it's going to be 1.73. To get that fixed.
This particular example is for a 700 kPa QRPT. Do you have an uncertainty analysis for other ranges of QRPT for QBTs? Yes, there's a guide on a website called Guide to Determining Pressure Measurement Uncertainty for QRPT-based products. It's available that goes into much more detail on the QRPT. There's also a patient available, or a pay available on the uncertainty of the cordon tube as mentioned in the user manual for that product. The next question to explain that in more detail.
For that question, the Degrees of freedom is the number of measurements that are performed minus the number of independent variables in the equation. So one independent variable, like if you have x, and with 10 measurements, the degree would be 10 minus 1, which would be 9. Simplistic explanation. Another example, I see when you have if you're plotting a line which has dependent variables x and y, and you have 10 measurements on that, your degree would be minus 2, which would be because you have 2 independent variables. Pretty much the more degrees of freedom you have, the better average and more confident of your measurement of your average, your mean, pretty much. I think GUM says if you have the guide to uncertainty of measurement in section G 3.3, freedom V equal to n minus 1 for a quantity estimated by the arithmetic mean of the independent observations. The clear-cut, or I was trying to find a diagram for degrees of freedom, but really it's the number of measurements minus the independent variables in your equation.
Generally, the more data you have, the better you are. Here, there's one that's more deadweight tester related. For deadweight tester, what resolution do we need to take? For those that aren't as familiar with the product, ones where pressure is determined by floating piston with a force applied to it, so it's force divided by area. There's no out of the pressure. The pressure is calculated the force of the created by the masses divided by the effective area of the piston. So resolution doesn't really play into it as much. You have terms of sensitivity, which is basically looking at what smallest mass that you can apply to the tester and have a change in the input of the deadweight tester. The question also asks, can you provide the spreadsheet you use? Does it cover 7250 XI? Yes, we will be providing that the follow-up email. Does it cover 7250 XI controllers? Not because as far as the terminology of QRPT span and so forth, but the components are very much the same. Modded for use with the 7250 XI.
Any examples or questions, if you have any budget you want me to look at, you can always email me. Direct email address is in the slideshow that will be emailed out. So feel free to me any questions you have regarding any uncertainty budgets you're working on, and I can try with you within a couple of days, hopefully, how in-depth the question is. And that's the question asked for the date pressure gauge and resolution. Till you have a calibration of your masses, you have your mass resolution, and then you have using trim mass. That really determines how well you can calculate or measure your pressure. If you're using some software to figure out your pressure, like Pascal or your own spreadsheet, it's typically based on what Tim said is your sensitivity of the lowest mass you can, your sensor of your mass, and the resolution of your mass.
Have any further questions? to email directly. An email will be going out with a follow-up with the copy of the presentation and a link recording. This is our last pressure webinar for the year. Thank you for throughout this year. We will have webinars after the first of the year. Thank you and have a wonderful day.